Let's take a look at how to solve exponential equations. And exponential equations are where the variable is in the exponent, okay? And before we get into the examples, the main idea here that we'll be using is that um, logarithms are the inverses of exponentials, okay? So in other words, um, if we apply a log to an exponential, it will undo the exponential. So, uh, so if I remind you, if I've got something like 2 to the a power, well, if I apply a log base 2 to that, then what happens is my log base 2 and my exponential in base 2 cancel, leaving behind the answer of just a. So the log base 2 canceled the exponential in base 2. Similarly, if I have 3 to the b power, I can undo that by applying a log base 3 to this expression, and that's just going to give me b. And so just a couple more here. If I have a base of e raised to the c power, then I'd have to apply a log that has base e. Well, that's the natural log. So I'll take the natural log of this, and that will give me c. And the last one is if I've got a base of 10 raised to the power of d, then to undo that I apply log base 10, which we just write as log. Okay? So if you want to undo an exponential with a particular base, apply the logarithm with the same base. Natural log is base e and log is base 10 with no subscript written. And those will undo your exponentials. So let's see this in action now if I want to solve some exponential equations. Let's say I want to solve the equation 5 to the x minus 3 equals 7. Okay? Now, I know I can undo this by applying a log base 5 to it. And I want to do that because my variable is in the exponent. So what I need to do is apply a log base 5 to the left side. But now to keep the equation balanced, because in this problem I'm working in the context of an equation, I have to do the same thing to the right side. So I have log base 5 of 5 to the x minus 3 equals log base 5 of 7. And on the left side, my log base 5 and my exponential in base 5 cancel, leaving behind just the exponent x minus 3. And on the right side, I've got log base 5 of 7. We're almost done now. The exponential's gone. My variable is no longer in the exponent, so solving for x is much easier now. And I would do that by adding 3 to both sides. So I'd have x minus 3 plus 3 equals log base 5 of 7 plus 3. And on the left side, I just end up with x, and on the right side, I have log base 5 of 7 plus 3. Now for the calculator, if you wanted to get a decimal, so this is our final answer. Oftentimes we're asked for an approximate answer, so we'll use a calculator to approximate if we're required to. Two different ways. You could type in log base 5 parentheses with a 7 inside plus 3. And it's important to understand that in this expression, the only thing you're taking log base 5 of is the 7. So this whole thing is one expression. You calculate that, and then you add the 3. So some calculators, you can do this. Other calculators, you cannot type in log base 5, okay? So you could do that with the change of base formula. So log base 5 of 7, you could type this in if your calculator can do that, or you'd have to use the change of base, which tells you that this is the same thing as the log of 7 divided by the log of 5. So the yellow thing could be calculated in both of these ways depending on your calculator. And then you'd have to add 3 to that. So in either case, you plug either of those into your calculator, whatever you can do on your calculator, and it looks like we get approximately x would be equal to 4.209. So this is the approximate answer. This over here is the exact answer. The exact answer does not require you to write a decimal at all. The exact answer tells you how to find the approximate answer yourself. So you could type this in somehow to calculate your approximate answer. Let's see another example. E to the 5t equals 300. My variable is in the exponent of e, and to undo a base of e, I apply a natural log to both sides. I have to do it to both sides to keep it balanced. So on the left side, my natural log, which is base e, cancels with my exponential in base e, leaving 5t, and on the right side I just have the natural log of 300. Feel free to put the parentheses around the 300 if you prefer that. Textbooks often don't do that. Finally, to get t by itself, divide both sides by 5. Because 5 is multiplied by t, so we get rid of it by dividing by 5. So t equals the natural log of 300 divided by 5. So there's our exact answer. If you want to calculate it in a calculator, any scientific calculator should have a natural log button. So you probably would need parentheses around the 300 and divide that whole thing by 5 to get approximately 1.1408. Okay? So x is approximately 1.1408, or exactly natural log of 300 divided by 5. Sorry, my variable is not x, it's t. There we go. Now in this example, I need to undo this guy. Need to undo that, right? To get t by itself. So if I want to undo this, this 1000 is in my way. I need to get rid of my 1000 first. And since 1000 is multiplied by this thing that's circled in red, I need to divide both sides by 1000 to get the red thing by itself. So I've got 1000 e to the 0.9 t equals 5000, and I'll divide both sides by 1000. And so what remains on the left side is just e to the 0.9 t, and on the right side I have 5. Now I can go about taking the exponential apart. The idea is you always want to isolate the thing that you need to work on. In this case, the 1000 wasn't a big deal. You could get rid of it, and then you could work on the heart of the problem, which was the exponential. So now I need to take the natural log of both sides to undo my exponential. So on the left side, I get 0.9t, and on the right side, I have the natural log of 5. And finally, to get t by itself, I need to divide both sides by 0.9. So t equals the natural log of 5 divided by 0.9. And if you wanted to, you could plug that into your calculator and get a decimal approximation. Let's look at one more example. Okay, so the thing I need to fix here, where I need to unravel my x, is right here. So I need to get this by itself. So I need to isolate this so that I can undo it to get x. So that means all of this stuff here needs to go away. So I start by first subtracting 1 from both sides. So I'll do minus 1 over here, and I'll have minus 1 over here. So we've got 1 minus 3.9 to the x minus 1 equals negative 48 minus 1. On the left side, my positive 1 and my negative 1 cancel to become 0. And now I'm left with negative times 3.9 to the x equals negative 49. Now I need to get rid of this negative that's multiplied by 3.9 to the x, so I divide both sides by negative 1. Then I have positive 3.9 to the x equals positive 49. And now I need to undo a base of 3.9, so I need to take log base 3.9 of both sides. And let me move this over. Maybe I should have written a separate step for this, but this works as fine as 2. So log base 3.9 of 49. On the left side, I just end up with x, and on the right side, I've got log base 3.9 of 49, and we're done. Now, that's because x is by itself. I didn't have to do any more work to get x by itself at that point. If you wanted to do this in a calculator, type this in directly, or use your change of base formula to do log of 49 divided by log of 3.9, which appears to be approximately 2.860 when you plug that into a calculator to get an approximate decimal. So the idea is, in summary, get the exponential by itself. So in this problem, the exponential is the 3.9 to the x. I needed that by itself. Or in this problem, it was e to the 0.9t. Get that by itself. Get the exponential by itself. Then undo it using the appropriate logarithm. And that's it, okay? Then you can finish getting x by itself very easily. To calculate an approximation, you may have to use the change of base formula depending on your calculator. Okay? So that's how you solve exponential equations. Go practice with it, see how you do.